Hi, we're going to look at this same integral again that we've been looking at in the last few videos and talk about an even more effective way to get a numerical approximation for this integral. The method that we're going to use this time is called Simpson's rule. Simpson's rule is based on using parabolas to estimate the shape of the curve and finding areas under parabolas. Your textbook goes through the development of that. But for the most part, probably you should plan to just memorize this formula for Simpson's rule. So I'm going to put it here on the screen, and then we'll kind of talk about some patterns in it so that hopefully that makes it a little bit easier for you to memorize. Okay, so here is the formula for Simpson's rule. It says as long as our function is continuous on our interval, which ours is, then the integral is approximately equal to this sum. So we're going to do Simpson's rule for n equals 6. So we're going to partition our interval into 6 pieces here. So we'll have from y0 to y6. Just like we did on our last one, we can figure out the delta x there by taking the width of the entire interval, which is 3, to minus -1, which is 3, and dividing that by how many pieces we want to divide it up into. And so we'll get 0.5. So that's our delta x that we're going to use. Because of the patterns in the formula for Simpson's rule, you actually need to ensure that the n that you're using for Simpson's rule is an even number. So your textbook or homework should never ask you to use Simpson's rule for an odd n value. The patterns in the formula require an even n value to work out. But since we have an even n value here, we can go ahead and do Simpson's rule with n equals 6. Alright, so we're going to be using this formula that we have here, and in the last video I used the table to help a little bit with the organization and multiplied my y values by the appropriate coefficients. So one thing we want to pay attention to here is the pattern in those coefficients in these y values kind of on the inside terms on this sum here. Alright, so the textbook goes through the development of this formula and why these coefficients are the way they are, but I find it's kind of a long derivation of that, and so most students, I think, find it a little bit easier to just memorize the pattern here. Alright, so we have 4, 2, 4, 2 for the coefficients ending with 4. Remembering that just like in trapezoidal rule, the ones that we have on each end here don't have a coefficient written in front of them, so we can think about that being a coefficient of 1. So just like I did on the last video, I took my y values in my table here. I have my table set up here with a partition of width 0.5, so all these x coordinate points are 0.5 units apart, and so these are the same y values we need here. And so what I did in the last table was I just wrote multiplication by the appropriate number. We had all 2's and 1's for trapezoidal rule, but for Simpson's rule we've got some 4's here. And so if you can just kind of remember the pattern and remember how it starts, 1, 4, 2, and then you're alternating 4 2's here, and that you should end with 4, 1. If you can remember how that starts, that will help you get the sum that you need is inside the box here. So this formula probably does require a little bit of memorizing, a little bit of practice making sure you can write this down. Alright, so we're just going to go ahead and do these multiplications. 2.06 times 4, 8.24, 2 times 2, 4, 1.06 times 4, be 4.24, negative 0.6 times 2 would be negative 0.52, negative 1.29 times 4 be negative 5.16, and then of course multiplying by 1 doesn't change anything, but just writing it like this helps keep everything lined up. Alright, so then we're going to add up all those numbers, and so get out your calculator for that. You should get 10.58 when you add all those numbers up, and then that number that I came up with there is the sum that I get from everything that I put a box around in my Simpson's rule formula. So using that Simpson's rule formula, my delta x is 0.5. For Simpson's rule, we're dividing by 3. That has to do with the derivation of the formula that's in your textbook, why it's divided by 3 there. And then times the sum that I got here from adding up all these numbers times 4s and 2s. So times 10.58. All right, so go ahead and type that into your calculator. When you do that, you should get 1.763 repeating. And so that is an approximation for the integral that we started with here, wanting to approximate. So not exactly the same as the integral we started with, but a pretty good approximation. And actually, of the approximations we've done so far, that's actually the best approximation. It's pretty close to the one we got with trapezoidal rule, but it's actually just a little bit more accurate in some digits here at the end. All right, so if I did Simpson's rule with an even larger value of n, I should get an even better approximation. The other thing that you'll see in some of the other videos is how to use the numerical integration features that are built in on your calculator to get an even more accurate approximation. So the textbook doesn't cover those, so be sure you watch those videos about how to use numerical integration on your calculator.